Hello, this clip covers introducing you to haloalkanes. We're going to look at a number of different areas, some of which you've heard of before, and it's designed to get you started on your work on haloalkanes. So I'll be looking at naming, classification and reactivity, and it assumes that you'll know about electronegativity and polarity from your work before. So you may want to have your flashcards from before on electronegativity and polarity. So let's first of all look at how we name haloalkanes. So all haloalkane is an alkyl chain with one of the hydrogen atoms substituted for fluorine, chlorine, bromine or iodine. So let's have a look at an example. So, with bromoethane we have the fully displayed formula, and if we wanted to do the skeletal formula, we'd write this. So in other words, we'd have the carbon-bromine bond here, and we'd have the carbon-carbon bond there. If we wanted to draw the structural formula, you'd simply write this: CH3 CH2 Br. Okay, so what would happen if we added another bromine onto that? So let's get rid of our skeletal formulas. And our structural formulas, and make some room to do that. If we now had the same molecule, which is your ethane alkyl chain, your carbon skeleton, but this time we put two bromines on one of the carbons. That would now look like this. So we've named those two versions we just looked at, bromoethane or 1,1-dibromoethane, in the same way you do 2,2-dimethyl, you do 2,2-dibromo, for example. So I'm going to put a few other examples in the bottom left-hand side of the screen, just so you can see how the naming system applies. Right, so I've put in some structural formulae. Why not pause the video and see if you can name them, and maybe even draw out the skeletal or displayed formulae. I'm going to put the names up in a second, so pause the video and see if you can name those first of all. Okay, did you get those right? Let's have a quick look through them. In the first one, the bromines are on the second carbon, so whether the carbon on the left or the carbon on the right is carbon on one doesn't matter. There's two of them. So basically, that means there's two bromine atoms present, so the two numbers give it to you. In the next one, 1-bromo-2-iodo, this is carbon number 1, and this is carbon number 2. because bromine starts with a B, iodine starts with an I, sorry. So alphabetically, bromo will come before iodo, so where the bromine atom is substituted will be carbon number 1 automatically. In the third one, this is carbon number 1, and this is carbon number 2, because the carbon where all of the, or most of the substitutions are taking place, e.g. 3 chlorines all on 1 carbon, gives you 1, 1, 1. But then there's another chlorine on carbon number 2. So it's 1, 1, 1, 2. There's 4 chlorines in total, so we say tetra. So it's 1, 1, 1, 2, tetrachloroethane. So let's move on to classifying haloalkanes. So the classification here is exactly the same. So what we're looking at is the carbon attached to a halogen. We'll make it X. X can be Br, Cl, F, I, whatever halogen you want it to be. So if we have one R group coming off that, that's primary. So in much the same way, you can have secondary and tertiary. So now let's move on to the reactivity of haloalkanes. So the reactivity of haloalkanes depends on the polarity of the carbon-halogen bond due to differences in electronegativity. So if we look at carbon and chlorine, for example, if we put a bond pair on that bond, the electrons are going to be pulled closer to the chlorine than they are to the carbon. So if we put the permanent dipole in, it's going to look like this. So within a haloalkane molecule, you have this type of bond, a carbon-halogen bond. Obviously, that chlorine could be bromine, it could be iodine, it could be fluorine. The point is that all of the halogens are more electronegative than carbon, so therefore greater or lesser degrees of polarity are set up. So this means that haloalkanes are vulnerable to attack by nucleophiles. So I'm just going to put a quick definition up for a nucleophile. So if a nucleophile is an electron pair donor, it must have a spare electron pair, e.g. a lone pair that's available to be donated. So some of the common nucleophiles you'll come across at A level include NH3, ammonia, water, H2O, and the hydroxide ion, OH-. And the colon, or it looks like a colon, is actually meant to represent the lone pair. So the little colon that I've drawn next to specific atoms represents the lone pair that that atom, as part of the nucleophile, brings to the reaction. So we're going to look at a mechanism now called nucleophilic substitution. And that, as you'd imagine, is where a nucleophile substitutes for another atom or group of atoms on a molecule. So let's look at this particular reaction. If we have chloroethane drawn in its fully displayed form like this, and what we've got to do is we've got to draw in the dipole, and when we draw our nucleophile, which is going to be the hydroxide ion this time, we draw it like this with our lone pair of electrons, put the negative charge preferably next to the oxygen because that's where the negative charge is based. The first curly arrow moves from the lone pair round the back of the carbon. So due to the repulsion of the slightly negative chlorine for the negatively charged oxygen, the oxygen moves towards the back of the carbon, and then the carbon-chlorine bond breaks. And this is heterolytic fission because both electrons go on to the chlorine atom. So the next thing is that the OH bonds to the carbon, like so. This creates your ethanol. So new compounds formed. Chloroethane is turning into ethanol. And you also have a chloride ion. Notice how I've put a lone pair on the chloride ion. The chloride ion can actually behave like a nucleophile for exactly the same reasons as over on the left-hand side of the page in blue. So the chloride ion is released as a leaving group, and ethanol is formed. Okay, so that's your mechanism for nucleophilic substitution, and that's the main mechanism by which all haloalkanes react.